Good morning, everybody. I'm not sure I can give my talk. I'm still thinking about Jeff's talk. That's almost enough. We should take a break now. My head's spinning. Jeff, that was just absolutely fascinating. All right, my talk's a little bit less compelling, but I have about 4 important points that I'd like to make with a little bit of illustration. This is not an audience in which I have to explain the brain. I do talk to audiences in which that's news to them. Many of us here have known intelligent people, so I don't have to emphasize that. But this is a very exciting area, and if you can jump up to psychology for a moment, you know, we're all in this room, and something is really turning us on. Okay, it's not the same thing, but we're really fascinated. The structure of the neurons, or the way the neuron operates, or the psychology of the brain, or we don't care about the brain at all, but the fact is that is a piece of hardware. It does some amazing stuff, and it does it with very low power, specifically 20 watts, and it does in very small space, somewhere between 1,400 and 1,500 cubic centimeters. So I'm one of the boring people. I just want to give you my perspective, so if it's not yours, you can turn off. First of all, I am fascinated about high-performance computing. Now, I just came from a meeting in Portland, a SIAM meeting, in which trying to talk about anything other than MPI was considered radical and disruptive. All right, so I feel like the victim here. Now, the stuff I'm going to talk about is going to be, relatively speaking, slightly mundane, slightly pedestrian, but still important. So A, I'm interested in simply how to make computers orders of magnitude faster at a time when, as we've already stated, Moore's law is dying. The second thing is, as an application, so thinking is kind of cool. And but I look at thinking not as how a bunch of neurons are working together, but really what it is as an algorithm. So that's roughly what I'm going to talk about. So let's first define, I want to make a comment. So we are not the first to think about being inspired by the brain and to advance computing. Over the last 400 years, there have been many attempts, but it depended on, and here's one of the key points I want to make, the abstraction that someone defines or associates with the condition of the mind or the condition of the brain. And simply the ability to put 2 numbers together and come out with a third number repeatably was considered pretty impressive. And then 100 or so years later, being able to do this in a number of different ways, do this in a sequence, was pretty powerful, although technology wasn't up. And then, of course, there's the frauds who the chess machines and so forth back then. So before I go into the details, the notion of what in fact it means to be inspired. I love the term, whether it's neuronal inspired by neurons or inspired by the brain. I love the term because it allows us to define the notion of inspired. And this is giving us a flexibility and a breadth of perspective on this topic at an important time when we can look at it in many different ways. So when I think about this, I think about this notion of consciousness. And I differentiate that from thinking, and finally I think about the level of complexity that we've all been discussing today in terms of the brain structure. Now, while I'm conscious of thinking, I think I'm not going to talk about consciousness. So let me narrow onto the issues of thinking, and we identify many properties with thinking, but how to put it all together and get a machine that actually does what we would attribute to thinking is beyond this. You know, there's one word all today we haven't used in talking about machines that think, or machine intelligence, or some other phrase. The word understanding. What does understanding actually mean for a physical element, whether it's a computer with some software or ourselves in some way? I leave that open. All right, the extreme complexity, of course, is really tantalizing, and it's one that is defying the abilities of people who are building very large machines. So we've had more than enough discussion about the fundamental element, except we recognize that the fundamental element, the neuron, does provide a kind of abstraction. And we've had several talks that have gleaned from it certain specific, slightly simplified versions of what that abstraction is. And yet, we understand that it is not the pure abstraction of the neuron, but rather the interrelationship among neurons. That is to say, the local and relatively global context of those neurons that define what we're really looking for. And what is that? That's an emergent behavior. So almost no single neuron is terribly useful. It's their interrelationship in in and among themselves, both in space and has been discussed, and in time. So here's the one slide. So I want to use as the notion of a neuron-inspired or neuro-inspired, that we note that the fundamental element, the neuron, has both state and function, both internally within the neuron itself and at the interfaces of the neuron with other neurons. That when they are operating, they are performing independent, quasi-independent, but they're doing so both asynchronously, and I should mention slow, a millisecond. Well, I guess if you're doing it 100 billion times at the same time, that's pretty impressive with throughput. But a millisecond is 1,000,000 times slower than conventional, and 1,000,000 is an understatement, slower than the technologies that we use today. And so one of the things we should be thinking about is what is the abstraction that is, and this was a word previously used, invariant in achieving functions that we associate with thinking, such as processing streams of noisy data. And what is merely a byproduct, an artifact of the limitations of the manufacturing process, which in its own right can be fun, but the manufacturing process of the biological brain. So we have to differentiate between those, and we have to be smart enough to know which paths we want to exploit and be informed by, and which ones are rat holes we don't want to be dragged down by. It is almost ironic that the brain is also both incredibly highly connected and very weakly connected. There's 10,000, on average, right? It's already been stated, 10,000 connections for a neuron on average to other neurons. At the same time, they're on the order close to 100 billion neurons. And so the connectivity is like, and I hope I have the right number of zeros, but 0.00001% of the system. So those are two lessons to learn at the same time. And as I said before, we have to learn that the neuron and its, no doubt, its development, its evolution, is in the consequence and context of the rest of the neurons and the neuronal structures and the emergent behavior, that property, which in fact is what gets the feedback. Now, so I forgot which of our colleagues put up a picture of von Neumann and Oppenheimer standing in front of the IAS, 1952 with the year. There's more than one irony in the talk I'm going to give about von Neumann. One is the first von Neumann machine was not done by von Neumann, right? Wrote the paper, was on a train, when it was going to Los Alamos or someplace, forgot to put Eckert and Mauchly's name on that paper, so we have von Neumann architectures today. Perhaps that's a little bit snide, but in fact the first machines were out of the UK, the Manchester machine, late 48, the Cambridge machine, that's to say EDSAC, 49. But by the way, that's not the start of computing. Start of computing was a whole different class, a whole different strategy, and an important one for what we're trying to do. And that was the analog computer, sometimes referred to as Vannevar Bush machines by, Vannevar Bush, who was one of the principals in making them practical. They solve first-order differential equations. But what's interesting to us is that they have many of the properties, albeit abstract, that we care about. Individual devices that perform the functionality local and was connected potentially, though practically not so, potentially to a high order number of other devices as we're solving the set of first order, the array of first order differential equations. This has been manifest in many different technologies. The first machines in the 30s were electromechanical, passed then on to vacuum tubes, transistors, and finally in the 70s and 80s, op-amps. One of those machines that predated the IAS, by the way, was the Whirlwind computer at MIT, the same place that Vannevar Bush was at. And that machine, the Whirlwind project, many side effects, one of which was core memory, very, very important. The limitations of analog computers were simply the drift characteristics of putting too many states together. But what we're trying to do now, motivated or informed or inspired by neurons, we see those properties in previous machines. Now, it was mentioned previous neural network technologies. An earlier approach to developing this structure of localized operations interconnected with others. Goes back certainly to the 80s. The term distributed computing was used at that time, one of many abused terms. So many of the kinds of algorithms we're talking about now were explored by these systolic structures of these simplistic, and they were simplistic, neurons that began to explore the idea of training and weighting. Purely abstract, about the same time in the 80s, were expert systems, which, well, people get really psyched about their own ideas, right? And I remember otherwise really good people, and in publications, they wrote that expert systems capture knowledge that's impossible to put on paper. Yeah. Okay, I once met Claude Shannon, a very distinguished elderly gentleman, and he would differ about this. There are certain fundamental ideas of informatics that would be captured, but they were pretty excited about it. In any case, the expert systems allowed us to have local functionality in the abstract, a combination of conditioned statements and then following actions if the conditions were satisfied, and then a number of, and the others, those conditions were dependent on previous conditions. So you see a graph, and graph is a major and very important abstraction. You see a graph here of these localized computations and their interconnection. So it was really just a bunch of if-then-else clauses, right? But nonetheless, we get something like that. So I want to talk just a little bit about the work at Indiana University. And so I'd like to talk about, but these are illustrative of the other 2 points I want to make. And I want to talk about two. One is a very high-level problem. CRIS stands for Cognitive Real-Time Interactive System. Actually, the functionality that's already been kind of described. And the other, a very low-level, technology-motivated approach called continuum computer architecture. As you'll see in a moment, these are both related to, or at least potentially inspired by, the brain-inspired and neuron-inspired kinds of computing. And then I'm going to finish with a brief comment about the importance of abstraction in our considerations, and briefly mention one such abstraction. So I simply illustrate here that CRIS is a very high-level application, an intent to differentiate thinking or intelligence, treating it as an algorithm, from the myriad other properties that we associate with the mind itself. This thinking is only an element, an effect that humanity, the human condition, attempts to embrace. So I looked at some of the diagrams from Jeff's talk, last one, and especially these 2.5D arrays, and they said this is a great segue into what I want to talk about. Continuum computer architecture is a simple notion of localized functionality, and it's very easy to implement in this technology of today, which is coming to an end. And this is the cellular automata. So I mentioned there were ironies about von Neumann. Well, you can argue whether von Neumann invented the von Neumann architecture, but you can't argue about von Neumann inventing the non-von Neumann architecture, cellular automata. In some biographies, you'll learn that it really hurt him in order to make cellular automata meaningful. He had to prove that it was Turing equivalent. He would have much rather proved that it was von Neumann equivalent. But he didn't get that one. Gödel beat him out on another one as well. So much for mathematicians. I hope there aren't mathematicians in the room. So the thing about cellular automata, the positive, is that we can build lots and lots of them onto a single die, and somewhere in the order of millions of them. We don't generally do that, and principally because cellular automata, as originally employed, were used for special purpose applications where you were trying to emulate an effect as an emergent behavior. But when it came down to the numeric accuracy or so, it proved to be, in many cases, inadequate. Every once in a while, somebody would start a new company, and we've got the new answer to this. Well, cellular automata, one of its problems was its use is very, very elegant. You can go off and, there are enough old people. You remember the screen, right? The game of life, little things trickling across the screen, wasting hours watching that stuff and setting up different input patterns just to do this. Well, that, of course, is a simple case of cellular automata, but it really does represent this notion of emergent behavior as a property of local operations occurring, each one not really knowing about the rest of them. Well, one possible emergent behavior is not these special cases, but rather is in fact general purpose computing, and this would be general purpose parallel computing. When you build very large structures of this, you do exploit the physical property of nearest neighbor communication. But here's the special trick, and that is that the hard thing about building neuronal structures, by whatever technology you're using, is providing this dendrification, this interconnectivity by separate individual paths, whether they're metal or optical or biological, getting those all to work and then to be able to change them. This is going to be a real challenge to this field. But you don't have to do that. What you can do is do what a different technology like semiconductor is able to do. Pack lots of things densely, and then don't do line switch, do packet switching. And when you do that, this gives you the ease of manufacturing, the flexibility of programming, and at the same time it allows the morphability that you're going to need if in fact the connectivity itself is part of how information is both stored and filtered. So one of the things that we can do is be able to emulate these neuronal structures in 3D using an advanced version of cellular automata. It's a path that we're pursuing. I'm not going to claim success, and I simply throw it out as a possible consideration. Now let's jump to the other end, and that is another motivation, and we're motivated by intelligence, whether it's intelligence and a relatively tight algorithm special purpose, or intelligence broadly, the notion of learning and again use the word understanding. Now, I don't understand understanding, but I don't think it's simply, and this is simply a subjective notion, I don't think it's simply doing a histogram and finding where the statistical maxima are. Because there has to be an association back not just to the time sequence of a particular set of sensors, but to the much broader, and it was mentioned earlier, the broader notion of world. And so I think that there's more to understanding intelligence than simply figuring out those structures, as informative as it is. And this requires, however, an architecture, but an architecture which is more substantial and is functional. And you can even map that on top of the hierarchies that were discussed in more than one talk earlier today, in which we're dealing with knowledge and the processing of symbolics in large, another abstraction, graphed topologies. And another thing that was mentioned in one of the previous talks, we refer to it as objective function. An objective function is as important as the context at any point in time about any particular issue or set of channels. And in fact, objective function, the next thing that needs to be done, whether it's a macro thing like go find some place to eat lunch, to the micro thing that, how do you swallow food, is a hierarchy of objective functions that are constantly being processed. Now, I don't think we have exactly that kind of recursive mechanism going on physically in the human brain. Maybe wrong, somebody will correct me. But this duality of objective function and context, the local state, is a very powerful one that when they're bound together allows you to walk through workflows, and we've done this, walk through workflows to appreciate at least what we think are use cases of what we would all talk about as machine intelligence. And let me just jump next. Okay, so last brief topic is the issue of the abstraction that we refer to as execution model. And I've even seen this on a slide today. And this is where I think the heart of the issue ultimately comes down. Now, execution models are simply strategies or paradigms in how we organize automated computation. And it can be as simple as the difference engine that, beg your pardon, that Charles Babbage, developed, and the analytical engine that he failed to actually implement, but was duplicated a mere 100 years later by Aiken from Harvard. Just down the street from Harvard is where the whirlwind that was successful was done at MIT. I only mentioned that in passing. Yes, I did get my graduate degree from MIT. And the execution model over the last 60 to 70 years of digital computation has changed half a dozen times or so. And we are in the midst of a transition right now, deeply resisted by intransigent, albeit well-intentioned people in industry, academia, and even the labs, who are afraid, and the fear is not unjustified, that this will be to some degree disruptive in fulfilling the immediate obligations of the missions of the different agencies. An execution model that we've been using for purposes of experimentation, we dubbed Parallax for a parallel execution model, so that's redundant, I guess. And it has a small number of basic fundamentals, all of which have been seen in the prior art. It is simply the synthesis and some other nuances that provide any uniqueness of the Parallax model versus some of the other good work that's being done at other places like Rice and Lawrence Berkeley. And I'm sure MIT in terms of Silk, which is now at Intel, and Intel itself, and so forth. But what I found interesting about this was that these precepts, which address many critical performance problems, including problems of starvation, latency, overhead, and contention, the delays for access to shared resources. These basic precepts, which involve the use of concurrent threads, no surprise, Burton Smith, the use of not just message passing, but message-driven computation, the use of special local but rich synchronization constructs, and the use of a context, an abstract context of a global namespace. And what it turned out to surprise me was that there is a direct isomorphism of those basic precepts to, in fact, the neuronal structures. Now, I may be guilty of oversimplification because I'm trying to shoehorn something, but I assure you it wasn't my intent. As I was preparing the talk, I started thinking about this. And so, indeed, the neurons can be represented by the compute complexes, those being instantiated threads, and perform those local operations, while the parcels, which are packet switched, can, in fact, represent the interactions, the connectivity, that can, the connection patterns of which can change over time, but they provide not just messages, but they're the event-driving aspect of the computation, which in this case can be the emulation of neurons. The local control objects actually address or respond to the asynchrony that exists in the brain as well as potentially in other circuits, very large machines, and they define the satisfiability constraints for firing that is intrinsic to neurons. And finally, the context, the global address space, which in the case of neuronal systems can comprise the brain, but it provides a single global context in which the connectivity can change in time. And I suggest that this software, by the way, exists as a runtime system in a very low-level programming interface, and we're using it to explore future scalability and efficiency issues into the extreme scale and exascale era. Nonetheless, I see a direct relationship of this model to possibly the emulation of neural structures. This is a new idea for me, and I share it with you. So in summary, we recognize, and it's been hard coming, that not only is Dennard scaling gone, and that certainly was in the 2005 timeframe or so, but we are nearly at the end of Moore's law. If you want to talk about the exact slope that Gordon Moore proposed, then we're at the end of Moore's law. We're still in a growth stage, but we're going over the top of the S curve. And if we have to, if those who are really not willing to give up, we'll hold off until 5 or 7 nanometers, then we have a few more years to go. The Neuroinspired computing and this notion of the computational elements come from that, have direct applicability to general purpose computing and possible future high performance computing beyond the von Neumann era. You may call this the neo-digital era, before we even move to different technology trends. The new technologies themselves are advancing the new opportunities. And it's a closed loop. Execution models themselves have changed in response to, even as they have served, the new opportunities and challenges provided by those technologies. So the revolutionary times that are in front of us, I see as a transition of the new algorithms that are motivated and inspired by the work being done by this community, and eventually more and more, quite possibly, of the architecture and even technologies may ultimately be from the biological period and the neuronal structures. I don't know. But much of what's been discussed today and will be discussed in the next 2 days can be implemented immediately now by making adjustments on otherwise conventional technologies. And I have really high hopes for a motivation of the transition that has been difficult to start, but now is taking off and is accelerating. Thank you very much. Yes, Dave.
So one of the themes that we're supposed to be thinking a little bit about, which is actually the sort of area I'm coming from, is the application space. And of course you come from the application space of traditional high-performance computing. We've had some speakers talk about we need to be focusing neuromorphic computing essentially on things that traditional computing just can't do. My question to you is, do you see any sort of bridge where there are certain things that traditional computing can do, maybe not really well, but that the neuroinspired computing might actually be able to do significantly better as opposed to a completely different area of application?
Well, yes. Not enough time to talk about all of these. I actually pulled a couple of slides, but dynamic graph processing is that bridge. What you are often describing in this community to duplicate much of what the brain suggests would be done can be represented or described as graphs. Graphs are differentiated from the conventional sparse and dense matrix representations of most more conventional applications, numeric computations. Though I have to say that graph processing also has significant impact in things like adaptive mesh refinement and various particle codes and so on, as we have to change the relationship between the computation and the physical underlying computing medium. So it is the abstraction of the graph, and I began this talk by talking about abstraction, so I'll answer your question. It's the abstraction of the graph that allows us a means of mapping the problem of brain-inspired computation to the physical, today's physical computing media that I think gives us a potential lingua franca for representing these problems.